language.
Yeah. All right, hi, can everybody hear me? Yes. Okay, great. Yeah, so I'm going to explain in this talk what Seminaive evaluation is, if you don't know, and I hope by the end you'll have a rough idea how you can do it for a higher order language. But first, a pop quiz. What do the following have in common? Reachability in a graph, matching regular expressions, and abstract interpretation. If your mind immediately jumped to fixed points, then we're on the same wavelength. And if not, then I'll explain what I mean. Oh yes, the timer. All of these can be concisely expressed as fixed points of monotone maps, and they can be computed, at least in principle, by iterating those maps. And throughout the talk, I'm going to use graph reachability as a running example because it's the simplest of these to explain. So here's how to write graph reachability in one of my favorite languages, Datalog. You've heard a bit about Datalog if you went to the previous session. So Datalog is a logic language. We can just say what we mean. So for example, we're here declaring that start is reachable, right? And then we want to find all the nodes that are reachable from start in some graph. The graph is represented by some edge predicate. So we'll say that a node y is reachable if there's a node x that's reachable and there's an edge from x to y. So this is a natural recursive formulation. And Datalog will eat through this like it's nothing, right? It'll figure out which nodes are reachable. And in fact, Datalog is scalable to much more interesting programs, and it's found a niche being used to do scalable static analysis of large programs. But Datalog has a problem, which is if we want to do this for multiple different graphs, we have to repeat ourselves. Once for every graph that we want to find reachability in. And that's kind of annoying. If we were mathematicians, we just say, look, this is a function. It takes a set of edges. Why does this keep going down? It takes a set of edges. It takes a start node. And it finds us the reachable set as the fixed point of this function, right? As the set R that includes the start node. And whenever x is in the set R, and there's an edge from x to y, y will also be in the set R. So this is the same thing as Datalog, but written in different notation. And I look at this as a programming language designer and ask, what features do I need to add to my programming language to make this executable, to make this code instead of math? So we're using functions, so I'm going to start by using a simply typed lambda calculus. We're also using a finite sets and set comprehensions. And that's easy enough. We know how to represent finite sets as data, and we know how to implement set comprehensions as monadic comprehensions. That's well understood. We're also using a fixed point operator. It may be less obvious how we implement that. We'll get to that. I'd also like to note, if we're being pedantic, and we are, that in order for a fixed point to be well defined, there's various properties we need. And one of them is that the function we're taking the fixed point of is monotone. So as mathematicians, we can hand wave this, but a computer can't afford to be so cavalier. We need our type system to guarantee monotonicity. And at this point, I can reveal that I'm not talking about a hypothetical language. I'm talking about DataFun, which we introduced 4 years ago. And the way that DataFun guarantees monotonicity is, first off, to even say what monotonicity means, we need to interpret our types as partially ordered sets. So for example, our finite set type is going to be ordered by inclusion. To grow a set is to add elements to it. And to guarantee monotonicity, we're going to do something that may seem a little bit drastic. We're going to insist that all functions be monotone. And this is going to work out because the category of posets and monotone maps is Cartesian closed. So it forms a model of the simply typed lambda calculus. More informally, if all of your built-in functions are monotone, all of your definable functions are going to be monotone, because composing monotone functions makes other monotone functions. But you may complain and say, hold on, there are non-monotone functions that are important, like Boolean negation or set difference. How do we deal with those? And the answer is, we're going to internalize non-monotonicity using a comonad called box. And it's worth explaining that because it's going to be important later. So box A is going to represent a partially ordered set. The values of box A are going to be exactly the values of A. But the ordering is going to be different. The ordering on box A is discrete. Nothing is less than or greater than anything else. It's a very boring ordering. But it has the wonderful property that every function from box A to B is monotone. Every single one. And this is because it trivializes the monotonicity condition, right? if x is less than or equal to y at box A, that means they're equal. So of course f of x is less than or equal to f of y. They're equal. So in this way, we can treat non-monotone functions as a special case of monotone functions. OK, so let's go back to our reachability example. This is what it looks like in math. What do we need to do to turn it into data fun, to turn it into runnable code? Well, we need to add a few annotations having to do with monotonicity. In particular, we're not going to claim that this function is monotone, so we're going to box its arguments. This involves some term annotations that I'm going to ignore because they're not really relevant to the rest of this talk. We also need to be a little less cavalier about the fact that we're doing an equality test here, right? In math, we just use the variable twice. In data fun, we explicitly test equality. And that's it. This is now runnable data fun code. But how exactly does it run? How do we compute this fixed point? I said we were going to get to that. Well, let's take a closer look at the function, this function, that we're taking the fixed point of. Well, it looks like this. And one way to find its fixed point is just to iterate it. We start with the empty set, and we repeatedly apply the step function. And if we do that on a simple line graph of 4 nodes, and the start node is at the left, these iterations look like the following, right? In the first iteration, we discover the start node is reachable. And at every subsequent iteration, we extend the known world by 1 edge. And this is fine, simple, it's clear why it works, and it's terribly inefficient. The reason why it's inefficient is easily seen if we look at this second node. We discovered that this node is reachable on the second iteration by noting, via this set comprehension, the start node is reachable, and there's an edge from the start node to the second node. We rediscover that it's reachable on the third iteration for the same reason. The start node was reachable before, and there's an edge between them. And we rediscover it for the same reason on the fourth iteration. And if we had more iterations, we would keep on rediscovering it. So we're doing a bunch of redundant work between our iterations. And the amount of redundant work we do is going to be proportional to the number of iterations that we need to reach a fixed point. So this is asymptotically inefficient. In fact, this is quadratic. You can just add up the area covered by the sets. We know that we can do this in linear time. How would we do that? We'd do it by looking at the frontiers, right? We'd start by noting that the start set is reachable. Then the next frontier of reachable sets would be this one. Reachable nodes would be this one, and then that one, and that one. And this is a linear amount of work. So what would the code be for finding the sequence of frontiers, which I'm going to call dr sub I, for reasons I'll explain later? The first frontier is a gimme. It's just the start node. And then every subsequent frontier can be found by looking at all the nodes in the previous frontier, dr sub I, and looking at all the edges out of them. So now we have our set of frontiers, right? And this takes linear work to compute. And what I want to note now is that the step function is now irrelevant. We don't need it. Because what the frontiers really are, and why that I've called them dr sub I, is because they're the differences between our iterations over here. dr sub 1, for example, is the difference between R1 and R2. If you take R1 and union in dr sub 1, you get R sub 2. And so we can just union in these frontiers to find our known worlds. And this is the core idea of the evaluation strategy in Datalog called Seminaive Evaluation. And we've known how to do it in an automatic fashion since the 80s. It means finding fixed points faster by computing the changes between iterations. How do we do this for a higher order language, though? Well, for that, I claim we need a theory of changes for higher order languages. And there's a line of work on this that investigates something called the incremental lambda calculus. And an incremental lambda calculus, as we've applied it in DataFun, means that every type A gets a change type delta A, and the delta A type represents the possible changes to values of type A. And we formalize that using a relation that says, OK, the change dx turns the base point x into the updated point y. So for example, what are the changes to sets? Well, remember, the whole point here is to compute fixed points faster, and our fixed points are monotone. Our values only grow over the course of iteration towards a fixed point, so we only need to handle increasing changes. And an increasing change to a set is just a set of things you add to it. And our change relation tells us exactly that. Take a set x, to apply the change dx, union them together. We can also answer the question, what is the change to a pair? It's a pair of changes, right? And if dA turns A into A prime, and dB turns B into B prime, then the pair of changes dA dB will turn AB into A prime B prime. slightly more interesting, or perhaps more boring, is the type of changes to box A. So remember, box A was a type that was ordered discretely. There are no increases at the type box A. So the type of changes is the unit type. There's only one change possible, and it's to stay the same. And this is interesting because box A, from a perspective of monotonicity, was non-monotonicity. From a perspective of incrementality, it's not changing. Box A represents something that's not changing, and our types can guide our incrementalization. But of course, I've been putting off the most interesting change structure, which is the change structure on functions. Data fun is a functional language. How do functions change? Well, a function from A to B will change as follows. The change will be another function. It will take the original input. It will take a change to that input, and it will tell you the change in the output. What do I mean by this more formally is if you have a change, df, that turns f into g, what that means is whenever you have a change to the argument of the function that turns the argument x into the argument y, then we can find how fx, the original function applied to the original argument, turns into gy, the updated function applied to the updated argument. This is how we incrementalize function application. And we do it by taking df and applying it to the original input and the change to that input, just like I said up there. Now, I want to look at an interesting, or perhaps boring, special case of this. What if df turns f into itself? This is a little strange. This is a non-change. This is when f isn't changing. But even though f isn't changing, the argument can still change. And what df is telling us is how does f's output change as its input changes? And this should sound a little familiar. This is exactly what we needed for our Seminaive evaluation. We wanted to know how does the step function change over time as we iterate it. And in this case, we're going to call df the derivative of f, because it tells us how f changes. So suppose we have some step function, like our step function for our reachability example, and we have its derivative. Its derivative will take an original input, which we can think of as the known world so far in our reachability example. It will take a change to that thing, which we can think of as the frontier. Remember, the frontiers were the changes between our iterations. And it will give us the change in the step function, and that will give us our new frontier, the next frontier. So we want to compute the sequence of R sub I of iterations of the step function, but we don't want to compute it by iterating the step function. Instead, we want to compute it by finding the frontiers, the changes between these known worlds. And these frontiers will have the property that they turn R sub I, the ith known world, into step applied to R sub I. And we're going to define these sequences inductively. The first one is a gimme. R sub 0 is the empty set by definition. dr sub 0 is going to be step of the empty set, because the empty set, we need it to satisfy this property, so we need dr sub 0 to turn R0, which is the empty set, into step of R0, which is the step of the empty set. So again, by definition, it has to be that. The whole point of having these frontiers is that we can union them in to find the next known world, so that's exactly what we do. And what we do to find the next frontier is we use our derivative. We give it the currently known world, we give it the frontier, and it finds us the next frontier. And this slide is the essence of Seminaive evaluation in a higher order language. The rest is details. And you'll find a lot of details if you read the paper. So to give a broad overview of our approach, to cash in this idea that we can evaluate fixed points faster by using the derivative, we give two static transformations on DataFun. The phi transformation annotates all functions used by a fixed point with their derivatives so that we can use this semi-naive fixed point algorithm. But I said there were details. One of them is we don't just need the derivative of the function we're taking the fixed point of. If it calls other functions to find that derivative, we need their fixed points. And what we actually do to accomplish this is we hijack the box comonad to propagate derivative information through our program. I can perhaps say a little more about that at the end if people are still interested. But also we need to find these derivatives. We do that using the transformation delta E. Delta E computes how phi E changes as its free variables change. So this is taken almost directly from the incremental lambda calculus work. But we needed to extend it to handle data fun, and in particular, we needed to extend it to handle set comprehensions. In some sense, that's the computational heart of these transformations, is how does a set comprehension change as its free variables change? More stuff that you'll find in the paper. Whoops. A use case for combining higher order functions and bottom-up fixed points. So this is something that only we can do, that data fun can do, that Datalog can't do. And we use this to, for example, implement regular expression matching as combinators. We also give some logical relations that prove phi and delta are correct. These are essentially elaborations on the validity relations, the update relations that we saw earlier, but expanded upon to handle phi and delta. We actually need some further optimizations in order to get the asymptotic speedups that we want. In Datalog, joins are sort of implicit, whereas in data fun, relational joins emerge as a consequence of having set comprehensions. But set comprehensions are much more free form than relational joins, so we have to do a little extra work that basically amounts to, if you have a for loop that unions a bunch of empty sets, that may as well be an empty set, so you don't have to do the loop. That's where the asymptotic speedup actually comes from, is not having to do loops. And we have some benchmarks. You can see the red line goes up and to the right, which is bad, and the blue line stays low, which is good. More seriously, we elaborate this on the paper and explain why and when you should expect to get an asymptotic speedup from Seminaive evaluation. It doesn't always help you. There are some programs that just don't need it. But when it does help you, it can help a lot. All right. And I'd like you to take a few things away from this talk besides understanding what Seminaive evaluation is. First off, as I sort of opened with, bottom-up fixed points are actually really cool and expressive. The example given here was kind of small, but people really do use this stuff. And as functional programmers, we're sort of used to saying, yeah, recursion. Recursion is a wonderful idea. Recursive functions let us compute a lot of stuff. Lazy recursive data structures let us compute a lot of stuff. There's another kind of fixed point, another kind of recursion out there, which is this bottom-up recursion. And once you start thinking of problems in this way, you may find it hard to stop. To compute them efficiently, we need to incrementalize the step function, and we knew how to do that in Datalog in the 80s. We now know how to do it for higher order languages, in particular for data fun. And one of the key ideas in getting this all to work was that our types let us control what things were allowed to change and how. For us, it was allow only increasing changes, but I think other projects on incremental computation might also be able to take advantage of this. They might also, it might be useful to have a type that inhibits changes, for example, which is what we have. That's all. Thank you very much.
Thank you. Are there questions? All right.
So your canonical example here was graph reachability.
Yeah.
But the idea of frontiers gets a little bit fuzzy when you have cycles, especially when what you're computing is more than just a reachability Boolean, but some other set. Can you say a little bit about how this works when you have a cyclic graph and you're computing something a little bit more non-trivial than is it there or not?
Yeah. If you have a cyclic graph, it will still work. There are some subtleties in how exactly you set up your iterations. I sort of had you just expanding the frontier. What you might want to do is expand the frontier and then cut off nodes that you've already reached. And that'll, I'm not sure whether that'll give you an asymptotic performance improvement. It would be nice to do some tests on that, but it will give you a performance improvement. And that's just a small change to your iteration. Does that answer your question?
Yes, thank you.
Okay.
In your graph reachability example at the beginning, I think you marked the input for the edges as not monotone, as having a box, but shouldn't it be monotone in that argument?
You mean this?
Yes, yes.
Yes. Yes, so technically that's monotone. So one of the details that I have elided is the fact that we use boxes to propagate information about derivatives, and this requires us to make the argument to fix have a box type. Fix is semantically a monotone operation,
Right.
but we add a box here for implementation reasons, and because box is kind of contagious, that means we also need to box these arguments because they're used inside the fix point. And
Is there some kind of semantic justification for that, or? for why you need to do that?
There's not a semantic justification, but there is an operational one. The operational one is, remember that we wanted to speed up fixed points by finding the derivative of the function. Well, we don't actually have a thing that finds derivatives. We have a static transformation that finds changes. And as we saw earlier, the change to a function coincides with its derivative precisely if the function isn't changing. That's when you get a derivative. And so putting a box on the argument to fix lets us ensure that the function you're taking the fixed point of does not change.
Okay, so you wouldn't be able to do the optimization basically if the
We wouldn't be
function
able
was
to do the
changing.
optimization
Okay.
if, right, maybe there's some
I
way to
see.
extend
Okay.
it, but yeah.
All right, maybe one more question. Jonathan, you had a question? Yes. Oh, okay. All right. Well, thank you so much. Thanks for the speaker.